and hello everyone. This is Dr. Ismail Butun from Chalmers University of Technology, Sweden. This is a collaborative work in between Chalmers University and University of Delaware from USA with my colleague Alparslan Sari. And the topic of my presentation is a highly scalable instruction scheduler design based on CPU stall elimination. And this is in this work our aim is enhancing the CPU efficiency by optimizing the compiler via techniques such as random scheduling and sliding window scheduling. So the outline of my presentation is as follows. So I will start with the problem statement and continue with the background on the topic, and I will proceed with the methodology on the topic on our design, and I will present our design, the details of our design, and I will proceed with the results and finally with the conclusions. So the problem statement, the compiler optimization is an important concept for the high performance required applications such as games, simulations, rendering, scientific calculations, or any computation intensive software. And even a fraction of performance improvement makes a big impact for high computation required software. And it is worth spending more time on code optimization in compile time to achieve performance improvement in runtime. So the question comes to why on earth we need a compiler optimization. Actually, no one would appreciate stalls while they are using an application. For instance, at the heart of a heated game, you will not appreciate any kind of a stall. And I believe you all experienced this kind of problems in your games in the past. And for example, in a kind of Godot game engine, you may experience stalls in the game, and this might give a really bad user experience for the game players. And therefore, we suggest that code optimization is a good investment for any kind of customers, including games, simulation softwares, and HPCs. And for commercial and popular applications, the kind of compiler optimizations will make each and every user's processor to work more efficiently. And the background on this work is all about instruction scheduling, and it's a complex search problem. And basic block scheduling for a multi-core CPU is considered as an NP-complete problem. And Malik et al. Presented basic block scheduling on Spec 2000 benchmarks and achieved performance improvements. And in another similar work on basic block study is proposed a block reordering algorithm, which is a greedy heuristic algorithm. And by identifying a set of features possibly influencing the performance and collective metrics to apply machine learning to find best optimization. And in another work, Zhang et al. Proposed a novel cross-ISI basic block similarity method and assembly instruction normalization to perform optimization. So in another work, Neves introduced a compiler-assisted data streaming method using static analysis and code transformations with an on-chip data streaming support. The proposed approach provides up to 26% code reduction and an average of 40% performance improvement. And in a similar work presented by Yin et al., they used parallelized compiler breaking applications in tiny tasks and exploiting parallelism in function calls, loops, and data locality. We believe that our framework can be integrated with other implemented projects, such as Trofin et al.'s proposed framework, to utilize machine learning techniques in LLVM as a real-world case study. In Ashuri et al.'s work, they have summarized and categorized the recent advances in using machine learning for the compiler optimization field, and especially on two main obstacles. The first one is selecting the best optimizations, and the second one is the phase ordering of optimizations. And in a final work by Gaddioli et al., they have stressed about the difficulties and configuring program parallelism and selecting optimal compiler options according to the underlying platform architecture. A runtime selection of the best configuration requires the insertion of a lot of glue code for profiling, and runtime selection, which represents a programming challenge for application developers. And again, within the same paper, they have presented a structured approach called Socrates, based on an aspect-oriented language, and a runtime auto-tuner as a mitigation candidate to this unique problem. And here is the hardware specs that we have used in this work. It's actually a CPU with 3.2 gigahertz CPU and 512 kilobyte L2 cache and 128 GPRS and 258 kilobyte of SRAM, and this specs actually belongs to a PlayStation. Actually, we had a PlayStation P3 in our lab, and we have utilized that device for this purpose. And the methodology, in the methodology part, I can tell that we have generated an assembly with static timing analysis, and we generated data dependency graphs, and we shuffled the instruction codes randomly, and then we used either sliding window or random shuffling approaches to achieve our goal. And finally, we evaluated the results and presented to you as follows. And here we would like to give you an example how this assembly file looks like. So this is an assembly version of hello world.c, and as you can see on the left, we see the instruction cycles in the processor, and on the right we see the assembly codes associated with the hello C world. And here, that's important to mention that these dashes belong to the stall situations that we want to avoid. And again, the design of our implementation is as follows. As I mentioned, we use the assembler outputs, and we use them as an input for data dependency graph generator, and which is somehow fed into the instruction scheduler engine, and that generates the output for the compiler. And here again, we see a futuristic application of our work, and our proposal is promising even for future applications. For instance, for cloud-based applications, our compiler mechanism is actually, as you can see, parallel processable for cloud-based compiler systems. And here we can see the assembly ordering example for our methodology. Here we can see that in the first example, the second instruction waits the results from the first instruction, so it cannot be optimized for compiler shuffling. But we can see that in some other cases, for instance, in the first application, the second instruction waits the first instruction to be completed. But in the second example, as you can see, that the third instruction waits the result from second and fifth registers. But we can see that the second instruction does not wait anything from the first one, and the first one is not related to the second one. So we can use the shuffling in between and the first and second instructions. Here some results from our work. As you can see that total instruction counts for various benchmarking files. And as you can see that the sliding window scheduler provides the best result as it swaps the neighboring and adjacent instructions. Here, the graph version of the same results, and again, we can see that the optimization is really works even for the random case. We have a significant improvement, up to 15% improvement on the efficiency of our compiler. So the conclusions. In this work, a highly scalable compiler instruction scheduler is implemented, and new scheduler logic or other optimization methods can be easily plugged into CIS framework, and machine learning-based schedulers can be implemented based on collected optimization metrics and program features that are collected from the cloud nodes. And therefore, CIS could be trained to learn which opcode shuffle is more effective or redundant. And with its distributed system support, it can be easily deployed to multiple cloud nodes based on the producer-consumer paradigm to reduce the optimization time drastically. And one producer can generate the basic blocks and distribute the cloud workers to perform instruction scheduling. And all consumers return the best optimized basic blocks to the producer back to reconstruction, the optimized file. And this work can be extended for other hardware architectures, not limited to SPU. And this is the end of my presentation, and thanks for your attention.
Thank you, Ismail. Thank you for the very interesting presentation, interesting work, and really fine results. Do we have any questions from other authors or the audience? Eventually, have you been thinking about proposing some similar solution like yours to the, let's say, to the commercial area, concerning that the universities of the US and the Sweden are pretty oriented towards let's say the wider usage of the solutions they develop? Yeah,
actually, we would like to extend this work. We ended up around PlayStation 3 era. Actually, we need to improvise it for the new versions of the processors. And also, as I mentioned, it's also cloud applicable. And so we are planning to expand this work over cloud providers as well. So it's an ongoing work, and we are very optimistic about this. And thanks for your question. It was really good.
Thank you, and we wish you all the good luck in the following steps in that direction.